Welcome to the Board of Small Wisdom. I'm going to start doing this occasionally for various topics. These videos will probably be only about 5 minutes long, but try to give some oral explanation of some key points. I'm not going to edit any of this stuff. It's going to be done in one take, just like in a regular classroom. So for today, I want to just do a little thing on the Board of Small Wisdom. I might actually randomly appear on camera, try to avoid that, about the inverse square law, because this is a relatively easy thing to understand, but students have struggled with it for generations, largely because you want to think about problems formulaically, like numbers to plug into an equation. That shows you can use a calculator, but little else, as opposed to thinking about how physical quantities scale with respect to one another. And if you can learn that skill, you can do math in your head easily. You can solve a lot of problems pretty fast. But basically, the inverse square law of light works like the following. Suppose I have a star. All stars look like that. And I've got some detector, which is going to detect the energy from that star at some distance d. And let's suppose I've got another observer elsewhere around this star that's got a detector at a distance of 2d. Well, suppose the flux, the amount of energy received per square centimeter per second on detector for observer A equals 100 flux units. We don't care what those units are in any absolute sense. They're just 100 flux units. Okay, well, this star has some intrinsic luminosity L. That can't ever change. That's the intrinsic energy output of the star. And since the flux of light falls off as 1 over d squared, then this detector, which is 2d from this star of luminosity L, will have a flux that's 1 over 2 squared less than a detector at distance d. So the flux at detector B would then be 25 units, because 100, that, divided by 2 squared, which is the differential distance. This distance is twice as much as that. 2d is twice as much as d. 2 squared is 4. That equals 25. And so this is the way that you would do any of these problems in this scaled way. So for instance, if detector B were located at 3d away, then received flux relative to detector A would be 3 squared less. 9 squared. 3 squared is 9, last time I looked. And so that would be about 11 in this case if it were 3D. So this is how flux and distance relate to one another when you're at different distances from a light source of constant energy output that's sending equal amounts of energy in all directions. As you move farther and farther away from that star, the amount of energy that you get from that star decreases by the square of the distance that you move from the star.